Before we begin, let me set the scene. The James Webb Space Telescope isn't just another piece of equipment floating in space. This is a machine that cost $10 billion and took over 2 decades to build. It's sitting a million miles from Earth right now, collecting light that's been travelling through the void for billions of years. And what it's showing us is deeply unsettling. Webb has been looking so far into space, so deep into the past, that it's seeing the universe when it was barely formed, when everything should still be simple and primitive. But that's not what it's finding. Instead, it's discovering massive, fully formed galaxies that are so large, so complex, and so mature that they shouldn't exist yet. Not according to everything we thought we understood about how the universe evolved. Tonight, we're drifting through discoveries that are forcing scientists to question the most fundamental assumptions about cosmic history. Things that, by all rights, shouldn't be there at all. So what exactly has James Webb been seeing that's got the entire scientific community reconsidering everything? Well, imagine you're looking back in time. That's essentially what this telescope does. The deeper it looks into space, the further back in time it sees, because light takes time to travel across cosmic distances. When Webb looks back to the very early universe, just a few 100 million years after the Big Bang, it should be seeing a dark, primitive cosmos, filled with small, simple galaxies that are just beginning to form their first stars. But that's not what it's finding. Instead, James Webb is discovering massive, fully formed galaxies that are so large, so complex, and so mature that they have no business existing yet. We're talking about galaxies that appear to have billions of stars, sophisticated structures, and masses that dwarf anything we predicted could exist in the early universe. It's like expecting to find a single-cell organism and instead discovering a fully grown elephant. Let me paint you a picture of just how shocking this really is. According to our best models of cosmic evolution, the universe went through what we call the Dark Ages after the Big Bang. This was a period lasting hundreds of millions of years where there were no stars, no galaxies, just a cold, dark expanse filled with hydrogen and helium gas slowly clumping together under gravity. The first stars weren't supposed to ignite until at least 400 million years after the Big Bang, and the first real galaxies weren't supposed to form until even later, as those early stars lived and died and their remnants came together into larger structures. The process should have been gradual, patient, taking billions of years to produce the kinds of massive, mature galaxies we see in the universe today. But Webb is seeing massive, mature galaxies when the universe was only 300 million years old. Some of these cosmic giants appear to have formed when the universe was barely 200 million years old. That's like finding a skyscraper in a neighbourhood where the foundation was just poured yesterday. The timeline doesn't add up, and it's forcing scientists to confront the possibility that everything we thought we knew about cosmic evolution might be fundamentally wrong. Here's where it gets even more troubling. These aren't just big galaxies. They're impossibly bright, impossibly massive, and they're everywhere Webb looks. When astronomers first started getting data from the telescope, they thought there might be a few anomalies, a handful of unusual objects they'd need to explain, statistical outliers that could be accounted for with some creative physics. But as more observations came in, they realised this wasn't a few outliers. This was the norm. The early universe is packed with these massive, mature galaxies that have no business existing yet. Not dozens, not hundreds, but potentially thousands of them scattered across every region of deep space that Webb examines. One galaxy that Webb discovered, designated JADES GS Z13U0, appears to have formed when the universe was only 325 million years old. But here's the problem. This galaxy is so massive and so mature that according to our models, it would have needed more time to form than the universe had actually existed at that point. It's like finding a 50-year-old tree in a forest that was planted 20 years ago. The math simply doesn't work. And this isn't an isolated case. Webb has found dozens of these impossible galaxies, each one challenging our fundamental understanding of how the cosmos evolved from the simple, uniform soup of particles that existed right after the Big Bang to the rich, complex universe we see today. Let me walk you through what makes these discoveries so deeply problematic. Star formation is supposed to be a slow process. You need enormous clouds of gas to collapse under their own gravity. These collapsing clouds fragment into smaller clumps that eventually become dense enough and hot enough to ignite nuclear fusion to become stars. But this process has natural limits. You can only form stars as fast as gas can cool and collapse. And in the early universe, with limited heavy elements to help that cooling process, star formation should have been even slower than it is today. Yet Webb is finding galaxies in the early universe that appear to contain stellar masses equivalent to tens of billions of suns. In some cases, these ancient galaxies contain as much stellar mass as our own Milky Way, a galaxy that's been forming stars for over 13 billion years. How is it possible for these early galaxies to accomplish in 200 or 300 million years what took our galaxy more than 13 billion years to achieve? The answer should be, it's not possible, not with the physics we understand. But there they are, scattered across Webb's deep field images, massive, bright, unmistakably real. One particularly shocking example is a galaxy designated Sears 93316. This object appears to contain over 100 billion stars worth of the mass, and it formed when the universe was only 235 million years old. The energy output alone is staggering. This single galaxy is shining with the brightness of 25 billion suns. The star formation rate required to build such a massive structure in such a short time would need to be hundreds of times faster than anything we observe in galaxies today. And it's not just the mass that's problematic, it's the maturity. These early galaxies don't look young and chaotic. They show signs of organization, spiral structures, central bulges, organized rotation patterns. These are features that should take billions of years to develop, as galaxies go through multiple generations of star formation, stellar death, and gravitational reshaping. But Webb is seeing these mature structures when the universe was still an infant. It's like finding not just a fully grown elephant, but an elephant with grey hair and wrinkles that indicate old age, when you're looking at a time period where elephants shouldn't exist at all. The spectral signatures are equally troubling. When Webb analyzes the light from these ancient galaxies, it's finding chemical signatures that shouldn't exist yet. You see, when the universe first formed, it contained only hydrogen, helium, and tiny traces of lithium. All the heavier elements, everything from carbon to iron to gold, had to be forged inside the cores of stars and then dispersed through supernova explosions. This process of cosmic chemical evolution is supposed to take billions of years. The first generation of stars had to live their entire lives, die in spectacular explosions, and seed the surrounding space with heavy elements before the second generation of stars could form with more complex chemistry. Each stellar generation adds more heavy elements to the cosmic mix, gradually enriching the interstellar medium until you get the kind of chemical complexity we see in modern galaxies. But Webb is detecting mature chemical signatures, oxygen, nitrogen, even iron, in galaxies that formed when the universe was barely old enough for even the first generation of stars to have completed their life cycles. One galaxy shows clear spectral lines indicating the presence of these elements when the universe was only 400 million years old. The problem is, based on our understanding of stellar nucleosynthesis and supernova rates, it should have taken at least 500 million years just to produce detectable amounts of these elements, even under the most optimistic scenarios. It's as if cosmic chemical evolution was fast-forwarded somehow, as if the early universe had access to processes that could accelerate stellar birth, life, and death, far beyond what our physics predicts should be possible. But the revelations don't stop with individual galaxies. Webb has also been discovering something else that challenges our timeline: ancient quasars. These are supermassive black holes that are actively feeding, surrounded by disks of superheated matter that glow brighter than entire galaxies. The problem is, these black holes are appearing in the early universe when they should be impossible to form. You see, supermassive black holes are supposed to be the end result of a long evolutionary process. First, massive stars form and die, creating smaller black holes. Then these black holes merge and grow over billions of years, eventually becoming the supermassive monsters we see at the centers of mature galaxies today. This process should take an enormous amount of time, but Webb is finding fully formed supermassive black holes when the universe was less than 1 billion years old, some appearing when the cosmos was only 400 million years old. One particular quasar that Webb discovered contains a black hole that's over 800 million times more massive than our Sun, and it existed when the universe was only 770 million years old. To put this in perspective, if the universe were a human lifetime of 80 years, this black hole would be like finding a fully grown adult when humanity was only 8 years old. The timeline is completely incompatible with our understanding of how these cosmic giants form and grow. There simply hasn't been enough time for normal processes to create something this massive. Some astronomers have proposed that these early supermassive black holes might have formed through direct collapse, where enormous clouds of gas collapsed directly into black holes without going through the normal stellar evolution process first. But even this exotic scenario has problems. You'd need very specific conditions, pristine gas clouds of enormous mass in just the right environments, and even then, the growth rates required to reach supermassive proportions in such a short time push the limits of what our physics allows. Every solution proposed seems to require the early universe to operate according to different rules than what we observe today. But perhaps the most unsettling aspect of all these discoveries is what they're revealing about our fundamental understanding of cosmic evolution itself. We built our entire model of how the universe developed based on observations of the nearby, modern cosmos, and on our understanding of basic physics. We watched how stars form today, how galaxies evolve over time, how structures grow through gravitational collapse, and then we extrapolated backward, assuming these same processes operated in the early universe, just with different initial conditions. But Webb is showing us that this assumption might be wrong. The early universe might not have been a simpler, slower version of today's cosmos. It might have been something entirely different, a place where matter behaved in ways we don't observe anymore, where processes operated at speeds we can't replicate, where the rules themselves might have been fundamentally different. When Webb's first deep field images were released, astronomers thought they might be looking at measurement errors. Perhaps the distances were wrong. Perhaps these galaxies weren't as far away, and therefore as young, as they appeared. But as more data came in, as distances were confirmed and reconfirmed using multiple independent methods, the reality became unavoidable. These galaxies are exactly where they appear to be, exactly as old as the measurements indicate, and exactly as impossible as they seem. The scientific papers started appearing with titles that reflected the growing bewilderment. A population of red candidate massive galaxies at Z6 with JWST, a high black hole to host mass ratio in a lensed AGN at Z4, spectroscopic confirmation of 4 metal-poor galaxies at Z10, each paper adding another layer to the mystery, each observation deepening the problem. At conferences, astronomers who had spent their entire careers studying cosmic evolution found themselves reconsidering basics. Assumptions, models that had seemed solid for decades were suddenly inadequate. Theories that explained the modern universe failed to account for what Webb was seeing in the ancient past. Some researchers started calling it the impossible early galaxy problem. Others referred to it more cautiously as tension between observations and predictions. But whatever you called it, the implication was the same. Something fundamental about our understanding of the universe was wrong. And the deeper Webb looked, the more apparent this became. The telescope wasn't just finding a few anomalies that could be explained away. It was revealing a systematic pattern of impossibilities scattered throughout the early cosmos. Every deep field observation brought new examples. Every spectroscopic follow-up confirmed details that shouldn't exist. The universe was telling us something important, something that challenged the very foundations of cosmology. But what exactly was it trying to say? That's the question that keeps astronomers staring at their data, searching for answers that might require rewriting everything we thought we knew about how the cosmos came to be. The timeline problem becomes even more stark when you consider what we know about the cosmic calendar. If the entire history of the universe were compressed into a single year, with the Big Bang occurring at midnight on January 1st, Earth wouldn't form until late September, complex life wouldn't appear until mid-December, humans wouldn't show up until the last few minutes of December 31st. All of recorded human history would flash by in the final seconds before midnight. It's a perspective that puts our cosmic youth into stark relief. But what about all those months before September? What was happening during the universe's long spring and summer? According to our models, not much. The first few 100 million years should have been a period of slow organisation, gravity gradually pulling matter together, the first stars igniting in isolation, small proto-galaxies beginning to take shape. It should have been the cosmic equivalent of watching paint dry, important foundational work, but nothing dramatic. Yet Webb is showing us something entirely different. The early universe wasn't quiet and gradual. It was explosively productive, churning out massive structures at rates that seem physically impossible. Let's talk about what these observations mean for our understanding of dark matter. Dark matter is the invisible scaffolding that holds galaxies together. We can't see it directly, but we can observe its gravitational effects on visible matter. About 85% of all matter in the universe is dark matter, and it plays a crucial role in how structures form. The standard model suggests that dark matter began clumping together first, creating gravitational wells that normal matter could fall into. Over billions of years, these dark matter halos would grow larger and more massive, eventually hosting the galaxies we see today. But this process has natural speed limits. Dark matter clumps together through gravity alone, and gravity is patient. It takes time for particles to feel each other's gravitational pull, to slowly drift together, to build up enough mass to attract even more matter. The mathematical models are quite specific about how fast this process should proceed, and those models tell us that the dark matter halos needed to host these massive early galaxies simply couldn't have formed in the time available. Yet there they are. Webb is seeing galaxies that would require dark matter structures far more massive and concentrated than our models predict should exist in the early universe. It's as if dark matter itself was behaving differently back then, clumping together faster, organising more efficiently, building structures on accelerated timelines that violate our understanding of gravitational physics. Some researchers have proposed that dark matter might have properties we haven't discovered yet. Maybe these invisible particles can interact with each other in subtle ways that allow them to cluster more quickly than pure gravitational models predict. Others suggest that the early universe might have contained a different mix of dark matter types, some fast-moving, some slow, creating a more complex gravitational environment than we see today. But these are speculative solutions to a very real problem, and every proposed explanation seems to require adding new physics that we've never observed. The alternative is even more unsettling. Maybe our entire understanding of how gravity works on cosmic scales is incomplete. Let me share another trouble in discovery. Webb has been observing what astronomers call the stellar mass density of these early galaxies, essentially how much star-forming material they contain, and what it's finding breaks every model we have. These ancient galaxies contain stellar masses that are orders of magnitude higher than what should be possible, given the amount of time available for star formation. In our own Milky Way, we form new stars at a rate of about 1 to 2 solar masses per year. That's considered fairly typical for a mature spiral galaxy. But some of these early galaxies that Webb has discovered appear to have been forming stars at rates exceeding 20 solar masses per year. That's more than 10 times our galaxy's current rate, sustained when the universe was still in its supposed infancy. The energy requirements for this kind of explosive star formation are staggering. You need enormous reservoirs of cold gas. You need gravitational forces strong enough to compress that gas into star-forming regions. You need complex feedback mechanisms to regulate the process, stellar winds, and supernova explosions that both trigger and limit further star formation. All of these components should take hundreds of millions of years to develop and organize themselves into the kind of efficient stellar factories that Webb is observing. But there they are, operating at full capacity when the universe was barely a few 100 million years old. It's like discovering a fully automated car factory in a world where nobody has invented the wheel yet. The implications extend beyond just star formation rates. These early galaxies also show signs of having gone through multiple generations of stellar evolution. Webb's spectroscopic analysis reveals the chemical fingerprints of stellar processes that should require sequential generations of stars, each one living, dying, and enriching the interstellar medium before the next generation forms. In our galaxy, this multi-generational enrichment has been happening for over 13 billion years, gradually building up the complex chemistry we see today. But Webb is finding similar chemical complexity in galaxies that formed in a fraction of that time. One galaxy shows spectral signatures indicating the presence of carbon, oxygen, and nitrogen in ratios that suggest the gas has been cycled through multiple generations of stars. But this galaxy existed when the universe was only 400 million years old, barely enough time for even one generation of massive stars to complete their life cycles. It's as if cosmic chemical evolution was operating in fast-forward mode, as if the early universe had found a way to compress billions of years of stellar birth, life, and death into a few 100 million years. Some astronomers have proposed that the first generation of stars, what we call population through stars, might have been dramatically different from stars today. These primordial stars, formed from pure hydrogen and helium, might have been far more massive than any stars we observe in the modern universe, and more massive stars live faster, die younger, and produce heavier elements more efficiently. If the early universe was dominated by these supermassive primordial stars, it might explain the accelerated chemical enrichment. But even this scenario has problems. We've never actually observed a population 3 star. They should have all died billions of years ago, and the theoretical models of how they form and evolve involve significant uncertainties. We're essentially proposing a type of star we've never seen to explain observations we didn't expect. Then there's the problem of galaxy morphology. When Webb looks at these early galaxies, it's not seeing chaotic blobs of stars. Many of them show clear structural features: spiral arms, central bulges, organized disk systems. These are the kinds of features that should take billions of years to develop. Our own Milky Way is a beautiful spiral galaxy with well-defined arms, a central bar structure, and an organized rotation pattern. But this structure didn't appear overnight. It's the result of billions of years of gravitational interactions, stellar formation and death, and the gradual settling of matter into stable orbital configurations. Computer simulations of galaxy formation suggest that these organized structures emerge slowly, through countless interactions and gradual gravitational settling. Yet Webb is finding galaxies with similar structural sophistication when the universe was young enough that there simply hasn't been time for these processes to occur. One galaxy that Webb observed shows a clear spiral structure with well-defined arms when the universe was only 500 million years old. According to our simulations, spiral arms like this should require at least 2 or 3 billion years to form and stabilize. The galaxy shouldn't look like this yet. It should be irregular, chaotic, still in the process of settling into its eventual form. But there it is, organized, structured, looking for all the world like a mature galaxy that somehow appeared fully formed in the early universe. Let's talk about something called the cosmic web. The cosmic web is the largest structure in the universe, a vast network of dark matter filaments connecting galaxy clusters across billions of light years. Galaxies aren't randomly scattered through space. They're organized along these filaments like beads on cosmic strings. This web structure is supposed to form gradually. Tiny density fluctuations in the early universe grow over billions of years, eventually creating the massive filamentary networks we observe today. The process is slow, patient, governed by the steady pull of gravity acting over cosmic timescales. But Webb is detecting signatures of cosmic web structure in the early universe when it should still be in the very beginning stages of formation. The telescope is seeing correlations between the positions and orientations of early galaxies that suggest they're already embedded in a web-like structure when the universe was less than 1 billion years old. This shouldn't be possible. The density fluctuations that seed cosmic web formation should be barely noticeable at this early epoch. The web should be just starting to take shape, with only the faintest hints of the structure it will eventually become. But Webb's observations suggest the cosmic web was already well developed when the universe was still a cosmic infant. It's another piece of the puzzle that doesn't fit. another indication that the early universe was far more organized, far more mature, far more complex than our models predict. Some cosmologists are now proposing that the initial density fluctuations after the Big Bang might have been larger than we thought, stronger seeds that could grow into mature structures more quickly. But this creates its own problems. If the initial fluctuations were strong enough to produce the structures Webb is seeing, we should observe corresponding features in the cosmic microwave background radiation, the ancient light from when the universe was only 380,000 years old. And we don't see those features. The cosmic microwave background is remarkably smooth and uniform, suggesting only tiny density variations in the early universe. There's a mismatch between what the microwave background tells us about the early universe and what Webb is showing us, happened just a few 100 million years later. It's like having a photograph of a perfectly smooth beach and then another photograph taken an hour later showing massive sandcastles. The two images don't tell a consistent story. Perhaps the most unsettling aspect of all these observations is their sheer consistency. If Webb had found one or two anomalous galaxies, we could write them off as statistical flukes or measurement errors. Even a dozen unusual objects might be explainable through exotic but rare formation scenarios. But Webb is finding these impossible structures everywhere it looks, in every deep field observation, in every spectroscopic survey, across vast regions of the early universe. The telescope has now observed thousands of early galaxies, and a significant fraction of them display characteristics that challenge our models. We're not dealing with rare exceptions. We're looking at a systematic pattern that suggests something fundamental about our understanding is wrong. At major astronomy conferences, the presentations about Webb's early universe observations have a common theme: disbelief giving way to acceptance, followed by urgent calls for new theoretical work. Astronomers are careful scientists trained to be skeptical, to question unusual results, to look for mundane explanations before accepting revolutionary ones. But the weight of evidence is becoming impossible to ignore. Something about the early universe was different from what we predicted. The processes that built galaxies, formed stars, and enriched the cosmos with heavy elements operated according to rules we don't fully understand. The question now is, what were those rules? Some researchers are exploring modifications to our understanding of dark matter. Maybe these invisible particles have properties we haven't discovered, interactions that allow them to clump together faster, to build gravitational scaffolding more efficiently. Others are investigating whether the physics of star formation might be different under early universe conditions. Perhaps with only hydrogen and helium available, stars formed more readily, burned hotter, evolved faster. Still others are questioning whether our fundamental models of cosmic expansion and structure formation might need revision. Maybe the universe didn't expand uniformly in all directions. Maybe there were subtle variations that affected how quickly structures could form in different regions. All of these are possibilities. None of them are proven. What we're witnessing is science at its most fundamental, observations that don't match predictions, forcing us to reconsider basic assumptions. It's uncomfortable, it's exciting, and it's deeply humbling, because Webb is showing us that the universe still holds mysteries we never anticipated, that our understanding, built up over decades of careful observation and theoretical work, might be missing something crucial about how the cosmos actually came to be. The telescope continues its observations, mapping deeper and deeper into space, further and further back in time. And with each new discovery, the picture becomes more complex. The mysteries deepen, the questions multiply. We thought we understood the story of cosmic evolution. We thought we knew how the universe grew from simplicity to complexity over billions of years. But Webb is suggesting the story might be different, more complicated, more mysterious, and we're only beginning to glimpse what that story might actually be. So what are scientists actually proposing to explain these observations? What theories are emerging to make sense of galaxies that shouldn't exist and black holes that formed impossibly fast? The answers being discussed aren't simple, and none of them come without significant complications. Let's start with one of the more conservative proposals. Maybe we've been underestimating the efficiency of early star formation. In the modern universe, star formation is a relatively inefficient process. When a giant molecular cloud collapses to form stars, only a small percentage of the available gas actually ends up in stellar form. The rest is blown away by stellar winds, supernova explosions, and radiation pressure from the newly formed stars. This inefficiency is built into all our models of galaxy evolution. But what if the early universe was different? What if, with only pristine hydrogen and helium available, the physics of cloud collapse operated more efficiently? Some researchers have proposed that without heavy elements, what astronomers call metals, gas clouds in the early universe could cool and collapse more readily. The absence of certain cooling mechanisms that depend on heavier elements might paradoxically allow gas to collapse more quickly under specific conditions. In this scenario, early galaxies might have converted a much higher fraction of their gas into stars, building up massive stellar populations much faster than later galaxies could. It's an elegant idea. It requires no new physics, just a recognition that the conditions in the early universe were genuinely different in ways that affected star formation efficiency. But there are problems with this proposal. For one thing, more efficient star formation should create other observable signatures that we're not seeing. If early galaxies were converting gas to stars at dramatically higher rates, they should be producing enormous amounts of stellar feedback, winds and radiation that would clear out surrounding gas and potentially shut down further star formation. We should see evidence of this violent feedback in the structures of these early galaxies. But many of them appear surprisingly settled and organized, not chaotic and disrupted. Another proposal involves the nature of the first stars themselves. The first generation of stars, what astronomers call population 3, should have been dramatically different from stars today. Formed from pure hydrogen and helium, without any heavier elements to catalyze nuclear reactions. These primordial stars might have been far more massive than any stars we see in the modern universe. Theoretical models suggest population egg stars could have reached masses of hundreds of solar masses, burning hot and dying young in spectacular supernova explosions that would flood their surroundings with the first heavy elements. If these supermassive primordial stars were common in the early universe, they could have accelerated both star formation and chemical enrichment. Their powerful explosions would compress surrounding gas clouds, triggering new waves of star formation. Their deaths would quickly enrich the interstellar medium with heavy elements. This could explain the rapid buildup of stellar mass and the surprisingly mature chemical signatures Webb is detecting. But again, there are complications. These population 3 stars, if they existed, should have left behind distinctive signatures, specific patterns of element abundances that reflect the unique nuclear processes inside supermassive stars. And while Webb has detected some unusual chemical patterns, they don't exactly match what we'd expect from a universe dominated by supermassive primordial stars. Moreover, we still don't fully understand how these population 3 stars would have formed in the first place. The theoretical models involve significant uncertainties about how pristine gas clouds collapse without the cooling mechanisms provided by heavier elements. We're proposing a solution based on objects we've never observed, using physics we're not entirely certain about. Then there's the dark matter problem. Remember, dark matter provides the gravitational scaffolding for galaxy formation. Visible matter falls into dark matter halos, where it can cool, condense, and form stars. The standard model of dark matter, called cold dark matter, assumes these invisible particles move slowly and clump together gradually through gravity alone. But what if dark matter isn't quite so simple? Some physicists are now exploring models where dark matter particles can interact with each other through forces beyond gravity. These self-interacting dark matter models allow for more rapid structure formation under certain conditions. If dark matter particles can collide with and scatter off each other, even weakly, it could change how quickly halos form and how concentrated they become. This might create conditions that allow galaxies to form faster and grow more massive than standard cold dark matter models predict. These self-interacting models have been proposed before, mainly to solve problems with dark matter distribution in small galaxies. But Webb's observations are giving them new relevance. If dark matter does self-interact, It could potentially explain the rapid formation of massive structures in the early universe. But there's a catch. These same interactions should affect dark matter behavior in the modern universe as well. And so far, observations of nearby galaxies don't show clear evidence of the kinds of dark matter interactions these models propose. We'd be explaining Webb's early universe observations by invoking dark matter physics that we don't see operating in the present-day cosmos. Another possibility being discussed involves the seeds of structure formation. Our models assume that the density fluctuations in the early universe, the tiny variations in matter density that eventually grew into galaxies and galaxy clusters, followed a specific statistical pattern predicted by inflation theory. But what if those seeds were different? What if some regions had larger initial density fluctuations than our standard models assume? Stronger initial seeds would grow faster, potentially producing mature structures earlier than our models predict. This is sometimes called the primordial power spectrum problem. If the spectrum of initial density fluctuations had more power on certain scales, if some seeds were stronger than others in non-random ways, it could accelerate structure formation in the early universe. The problem is, we measure this primordial power spectrum by observing the cosmic microwave background, and those observations suggest the initial fluctuations were quite smooth and uniform, following the patterns inflation theory predicts. To explain Webb's observations through stronger initial seeds, we'd need to propose that the power spectrum was different in ways that don't show up clearly in the microwave background data. It's not impossible, but it requires some careful theoretical work to make it consistent with what we already know. Some cosmologists are taking a more radical approach, questioning whether our model of cosmic expansion itself might need revision. The standard cosmological model assumes the universe has been expanding at a rate determined by its matter and energy content. This expansion rate affects how quickly structures can form. Faster expansion gives gravity less time to pull matter together. But what if the expansion history was different than we think? If the universe expanded more slowly during its first few 100 million years, it would give structures more time to form. Gravity would have longer to work, allowing galaxies to grow larger and more massive before the expansion carried them apart. The challenge is, our measurements of cosmic expansion are quite precise. We observe how fast distant galaxies are moving away from us. We measure the cosmic microwave background. We study the distribution of galaxies across cosmic time. All of these observations fit together into a consistent picture of expansion history. To explain Webb's observations through modified expansion, we'd need to adjust that history in ways that remain consistent with all our other measurements. It's a difficult balancing act. Perhaps the most intriguing proposal involves rethinking the nature of the cosmic dark ages, that period between the cosmic microwave background at 380,000 years and the formation of the first stars at several 100 million years. We've always assumed this was a quiet period, a time when the universe was dark and simple, with nothing much happening except slow gravitational collapse. But what if something significant was occurring during the dark ages that we haven't accounted for? Some researchers have proposed that there might have been exotic energy sources in the early universe, perhaps from dark matter interactions, or from the decay of particles left over from the Big Bang, that could have begun organizing matter before the first stars ignited. These pre-stellar processes might have prepared the universe for rapid structure formation once star formation began. Like seeds planted underground, invisible until they suddenly sprout. It's a speculative idea, but it has the advantage of explaining why structure formation seems to have happened so quickly once it got started. The early universe might not have been starting from scratch when the first stars formed. It might have already been partially organized by processes we don't yet understand. There's also discussion about whether feedback mechanisms in the early universe might have operated differently. In modern galaxies, star formation is self-regulating. When stars form, they produce winds and radiation that heat and push away surrounding gas, temporarily shutting down further star formation. Supernova explosions blast gas out of galaxies entirely. This feedback prevents galaxies from converting all their gas into stars at once. It creates a natural pacing to galaxy growth. But perhaps in the early universe, with different conditions and different stellar populations, feedback mechanisms were less effective. Maybe early galaxies could sustain high star formation rates for longer periods, without the self-limiting processes that govern modern galaxies. Or conversely, maybe feedback was more effective in specific ways, creating conditions that triggered bursts of star formation more efficiently. The physics of stellar feedback is complex and not fully understood even in modern galaxies. Extrapolating it to the early universe involves significant uncertainties. All of these proposals share a common feature. They're attempting to explain Webb's observations by adjusting specific aspects of our models while keeping the overall framework intact. They're trying to preserve as much of our established understanding as possible, while modifying the pieces that seem incompatible with the new data. This is how science typically progresses. When observations don't match predictions, you first try to adjust the details before questioning the fundamentals. But there's also a growing conversation about whether more radical revisions might be necessary. Some cosmologists are beginning to ask whether our entire framework for understanding structure formation might need to be reconsidered. Maybe the universe doesn't evolve in the linear, bottom-up fashion our models assume, with small structures forming first and gradually merging into larger ones. Maybe there are top-down processes we haven't accounted for, where large-scale structures can form directly under certain conditions. Maybe the relationship between dark matter, visible matter, and structure formation is more complex than our models capture. These are uncomfortable questions because they strike at the heart of the cosmological model that's been so successful at explaining observations for decades. But Webb is providing observations that are genuinely challenging, and the scientific method requires us to follow the evidence wherever it leads, even if it means reconsidering deeply held assumptions. What's particularly interesting is that different research groups are pursuing different explanations, each trying to solve the puzzle from a different angle. Some are focusing on the physics of star formation, others on dark matter properties, still others on cosmic expansion or the initial conditions after the Big Bang, and it's quite possible that the real answer involves multiple factors, that several of our assumptions need adjustment simultaneously to fully explain what Webb is seeing. The universe rarely arranges itself for our convenience. Complex phenomena often have complex causes. What's clear is that we're in a period of genuine scientific uncertainty, a time when multiple competing ideas are being developed and tested against observations. This is actually science working as it should. When observations challenge predictions, theories multiply. Different approaches are explored, hypotheses are proposed, tested against data, refined or discarded. Eventually, through this messy process of competition between ideas, we converge on explanations that actually work. But we're not there yet, not with Webb's early universe observations. We're still in the stage of proliferating hypotheses, still exploring different possibilities, still trying to understand what the universe is telling us. The one thing everyone agrees on is that something significant about our understanding of the early universe was incomplete. Webb isn't just adding details to a picture we already understood. It's revealing aspects of cosmic history that we didn't predict, that our models didn't anticipate. Whether the solution involves tweaking existing theories or requires more fundamental revisions remains to be seen. But the telescope keeps observing, more data keeps arriving, and with each new observation we get a clearer picture of what actually happened in the early universe. Whether or not it matches what we expected, the universe doesn't care about our theories. It simply is what it is. Our job is to observe carefully, think clearly, and adjust our understanding to match reality. Webb is giving us the observations. The careful thinking is now underway, and slowly, through the collective work of hundreds of researchers analysing data, building models, and testing predictions, we'll figure out what these observations mean. The answer might surprise us, it might require us to revise fundamental assumptions, but whatever it is, it will be based on evidence, tested against data, and ultimately more accurate than what we understood before. That's the promise and the challenge of what Webb is showing us. Not easy answers, but genuine mysteries that will push our understanding forward. Let's step back and consider what all of this means for our broader understanding of the universe. Because the implications of Webb's discoveries extend far beyond just the early universe. They touch on fundamental questions about the nature of reality, the reliability of scientific knowledge, and our place in a cosmos that keeps surprising us. First, there's the humbling realization of how much we don't know. For decades, cosmology has been considered one of the great success stories of modern physics. We developed a standard model that explained the cosmic microwave background, the distribution of galaxies, the expansion of the universe, and countless other observations. The model had 3 parameters that needed to be measured, things like the density of dark matter, the strength of dark energy, the expansion rate of the universe. But once those parameters were set using observations, the model made specific predictions about how the universe should behave, and for a long time, those predictions were remarkably successful. We predicted what the cosmic microwave background should look like, and when we measured it with satellites like WMAP and Planck, the observations matched beautifully. We predicted how galaxies should cluster together across cosmic distances, and when we mapped large-scale structure with surveys like SDSS, the patterns matched our models. We predicted how the universe's expansion should change over time, and when we measured distant supernovae, the observations fit our framework. This success bred confidence, a sense that we had the big picture right, even if details remained to be worked out. But Webb is showing us that perhaps we were too confident, that our models, tested primarily against observations of the relatively nearby, relatively recent universe, might not accurately describe conditions in the distant past. It's a reminder that scientific knowledge is always provisional, always subject to revision in light of new evidence. We weren't wrong to develop the models we did. They were the best explanations given the data available, but we may have been premature in assuming those models would accurately describe all epochs of cosmic history. The universe is under no obligation to make itself easy for us to understand. There's also a deeper question about the nature of scientific prediction itself. Our models of the early universe weren't just statistical fits to data. They were based on fundamental physics, gravity, thermodynamics, nuclear reactions, applied to cosmic conditions. When those models fail to predict what we observe, it suggests either that our understanding of the fundamental physics is incomplete, or that the early universe had properties we haven't accounted for. Either possibility is profound. If fundamental physics is incomplete, it means the laws we thought governed all of reality might have hidden aspects we haven't discovered, forces we haven't detected, interactions we haven't measured. If the early universe had properties we didn't anticipate, it means our picture of cosmic history has missing chapters. Processes that operated then but don't operate now. Conditions that existed briefly but left lasting impacts on cosmic evolution. Both possibilities point toward a universe that's richer and more complex than we realized. Let's consider what Webb's observations might mean for the concept of cosmic time. We tend to think of the universe's age as a simple linear progression, 13.8 billion years from the Big Bang to now, with each epoch following naturally from the one before. But Webb's observations suggest this linear narrative might be oversimplified. If massive, mature galaxies existed when the universe was only a few 100 million years old, it suggests that cosmic evolution didn't proceed at a uniform pace, that there might have been periods of rapid development alternating with slower phases. Or perhaps the very notion of cosmic time needs refinement. Maybe different processes operated on different timescales, with structure formation racing ahead, while other aspects of cosmic evolution proceeded more gradually. Time, on cosmic scales, might be more complex than simple linear progression. There's also the question of cosmic variance, the idea that the region of universe we can observe might not be representative of the whole. Our observable universe is vast, but it's still just a finite patch of what might be an infinite cosmos. And if different regions underwent different evolutionary histories, what we observe in one region might not apply universally. Webb's observations could be showing us that our particular cosmic neighborhood evolved in a way that doesn't match the average behavior of the universe as a whole. This wouldn't make our observations wrong, but it would complicate our ability to draw universal conclusions from them. It's like trying to understand Earth's climate by only studying one continent. You'd learn a lot, but you might miss important variations. Then there's the philosophical dimension to all of this. Throughout history, humanity has repeatedly discovered that we're not as central or special as we thought. Earth isn't the center of the solar system. The solar system isn't the center of the galaxy. Our galaxy isn't the center of the universe. Each of these discoveries required us to adjust our sense of cosmic significance downward, to recognize that we occupy no privileged position in the grand scheme. But what if our current moment in cosmic time is also not particularly special? What if the universe we observe, the one we've built all our models around, represents just one phase in a much longer and more varied cosmic story? The early universe might have been a place of frantic activity and rapid evolution. The far future universe might be a cold, empty place of isolated galaxies receding beyond each other's cosmic horizons. We happen to live in the middle period, a time when the universe is neither young and chaotic, nor old and empty, but somewhere in between. Our theories, developed from observations of this particular epoch, might not extrapolate well to very different cosmic conditions. It's not that we're wrong about what we observe, but we might be mistaken in assuming that what we observe represents some fundamental, unchanging cosmic norm. Let's think about what this means for the search for life elsewhere in the universe. One of the long-standing questions in astrobiology is why we haven't detected any evidence of alien civilizations. If life is common and some fraction of living worlds develop technological intelligence, where is everyone? Various solutions to this Fermi paradox have been proposed. Maybe life is rare, maybe intelligence is rare, maybe technological civilizations destroy themselves quickly. But Webb's observations add a new dimension to this question. If the early universe was capable of forming massive, complex galaxies far earlier than we thought possible, it means the conditions for potentially habitable planets might have existed much earlier than we assumed. Rocky planets with stable star systems could have formed when the universe was less than 1 billion years old, billions of years before Earth came into existence. If life emerged on any of those early worlds, if intelligence developed, if technological civilizations arose, they would have had an enormous head start on us. Civilizations that began their development when the universe was young would now be billions of years ahead of us in their evolution. What would such ancient civilizations be like? Would we even recognize them as alive? Would they still exist in forms we could detect? It's possible that the universe is filled with the descendants of these ancient civilizations, but they've become so advanced that their activities no longer look like technology to us. Or perhaps most early civilizations didn't survive. Perhaps the rapid, chaotic conditions of the early universe made long-term survival difficult. Webb's observations don't answer these questions, but they expand the possible timescales for cosmic intelligence in ways that make the Fermi paradox even more puzzling. There's also something profound about the fact that we're only now able to observe these distant early galaxies. For all of human history, the early universe was invisible to us. We could theorize about it, model it, make predictions, but we couldn't see it directly. Webb has changed that. For the first time, we have actual observations of what the universe looked like in its youth. And those observations are surprising. They don't match what we predicted. This raises an interesting question. What else have we been unable to observe that once we develop the technology to see it, will surprise us? Are there other aspects of the universe, other epochs, other scales, other phenomena that our current theories fail to predict because we simply haven't had the means to observe them yet? Webb reminds us that observation drives understanding. That theory, no matter how elegant and mathematically beautiful, must ultimately answer to what nature actually does. And nature, it seems, is fond of surprises. Let's consider the implications for dark energy, the mysterious force causing the universe's expansion to accelerate. Dark energy was discovered through observations of distant supernovae in the late 1990s. It came as a complete surprise to cosmologists who had assumed the universe's expansion should be slowing down due to gravity. Instead, the expansion is speeding up, driven by this unknown form of energy that permeates all of space. Dark energy is now a cornerstone of our cosmological model. We measure its properties, study its effects, and incorporate it into our theories of how the universe evolves. But we still don't really know what it is. We can describe its behavior mathematically, but we don't understand its physical nature. Webb's observations of the early universe might eventually provide new clues about dark energy. If structure formation proceeded differently than we predicted, it might be because dark energy's properties or effects were different in the past. Or perhaps dark energy isn't a constant property of space, but something that evolves over cosmic time, affecting different epochs in different ways. These are speculative ideas. But Webb is giving us observations that might eventually help constrain theories about dark energy's nature and history. The more we understand about how the universe evolved, the better positioned we'll be to figure out what dark energy actually is. There's also the question of what all this means for our confidence in science itself. When well-established theories fail to predict observations, some people take it as evidence that science is unreliable, that scientists don't really know what they're talking about. But that's exactly backward. The fact that scientists are carefully analysing observations that don't match predictions, revising theories, and openly discussing uncertainty. This is science working exactly as it should. Science isn't about claiming perfect knowledge, it's about developing the best possible explanations given current evidence, while remaining open to revision when new evidence arrives. Webb's observations aren't exposing a failure of science, they're demonstrating science's strength, the willingness to let observations challenge even well-established theories, and the commitment to following evidence wherever it leads. The discomfort scientists feel when observations don't match predictions is healthy. It's the sign of a discipline that takes empirical reality seriously, that refuses to force observations to fit theories when they clearly don't. This is how scientific understanding advances, through the productive tension between theory and observation, with each informing and constraining the other. What Webb is teaching us, ultimately, is that the universe still has the capacity to surprise us. That nature is more imaginative than our theories, that reality is richer than our models. These early galaxies, impossible though they seem according to our current understanding, are real. They exist. Webb has photographed them, measured their properties, confirmed their distances. Our models will have to change to accommodate this reality, either through refinements to existing theories or through more fundamental revisions. But whatever adjustments we make, they'll be guided by what the universe actually shows us, not by what we wished it would show us. There's something beautiful about this process, about the dialogue between human understanding and cosmic reality. We build models, make predictions, test them against observations. When observations surprise us, we revise our understanding and try again. It's humble work. It requires accepting that we might be wrong, that our clever theories might miss important aspects of how nature operates. But it's also powerful work, because through this process, however messy and uncertain, we actually do make progress. We actually do come to understand reality more deeply. 100 years ago, we didn't know galaxies existed beyond our own. We didn't know the universe was expanding. We didn't know about the Big Bang, or cosmic microwave background, or dark matter, or dark energy. Now we know all of these things, not perfectly, not completely, but genuinely. And we know them because we've been willing to let observations surprise us, to revise our understanding, to follow evidence even when it leads to unexpected places. Webb is continuing this tradition, showing us things we didn't predict, challenging us to think more carefully, pushing our understanding forward. The early universe might have been different than we thought. Cosmic evolution might have proceeded through pathways we didn't anticipate. But we're figuring it out, slowly, carefully, observation by observation. And in doing so, we're learning not just about the early universe, but about the nature of scientific understanding itself, about the value of humility in the face of cosmic mystery, about the importance of remaining open to surprise, about the power of careful observation to challenge and refine human knowledge. Webb isn't just a telescope, it's a reminder that the universe still has lessons to teach us, that reality is deeper than our theories, that the cosmos, for all our progress in understanding it, remains fundamentally mysterious, and that mystery, rather than being something to fear or avoid, is an invitation an invitation to keep looking, keep questioning, keep learning. The early universe holds secrets we're only beginning to glimpse, and whatever those secrets turn out to be, they'll be more interesting than anything we could have predicted. As we drift toward the end of this journey through Webb's discoveries, it's worth pausing to consider where all of this leaves us. We started with a simple observation. The James Webb Space Telescope has been finding massive, mature galaxies in the early universe that shouldn't exist according to our models. But as we've explored these discoveries, we've found that they point towards something deeper than just a problem with galaxy formation theory. They suggest that the early universe itself was a fundamentally different place than we imagined. Not just quantitatively different, not just a bit more active or a bit more efficient at forming structures, but qualitatively different in ways that challenge our basic framework for understanding cosmic history. The universe, at 300 million years old, wasn't just a younger version of today's cosmos. It was something else entirely, a place where processes operated according to rhythms we don't observe in the modern universe, where matter organized itself with an urgency and efficiency that seems impossible by today's standards. And we don't yet know why. We have proposals, hypotheses, ideas being actively explored by researchers around the world. But we don't have answers, not yet. What we have is a mystery, a genuine scientific mystery that will likely take years or decades to fully resolve. And there's something valuable about sitting with that uncertainty, about acknowledging that the universe has revealed something we don't understand, and that understanding it will require patience, creativity, and careful work. In our everyday lives, we're often uncomfortable with not knowing. We want answers, explanations, closure. We want the mystery resolved so we can move on with certainty. But science, at its best, teaches us to be comfortable with uncertainty, to be patient with questions that don't have immediate answers, to trust that careful observation and honest thinking will eventually lead toward understanding, even if the path isn't always clear. Webb's observations of the early universe are inviting us into this kind of patience. The massive early galaxies aren't going anywhere. They'll still be there, billions of light years away, while we develop better theories and gather more data. The universe isn't rushing us toward an answer. What Webb is doing now is what it will continue to do for years to come, collecting light from the distant cosmos, measuring spectra, recording images, building up a more and more detailed picture of what the early universe actually looked like. Each observation adds another piece to the puzzle, another constraint that theories must satisfy, another detail that helps narrow down which explanations might be correct. This is the patient work of science, not dramatic breakthroughs or sudden revelations, but the slow accumulation of evidence that gradually illuminates previously dark corners of understanding. There's also something profound about the timescales involved in all of this. The light Webb is collecting left those distant galaxies billions of years ago, long before Earth existed. It's been travelling through expanding space for most of the universe's history, carrying information about conditions in the ancient cosmos. And now, in this particular moment in cosmic history, that light is arriving at a telescope built by a civilization that only recently developed the technology to detect and study it. The timing is remarkable when you think about it. If we'd developed advanced telescopes a billion years earlier, we would have missed this light entirely. It wouldn't have reached us yet. If we'd waited a billion years, the expansion of space would have carried these galaxies even further away, making them even more difficult to study. We happen to exist at just the right moment in cosmic history to observe these ancient structures, to receive the light they emitted when the universe was young, to puzzle over what their existence means. There's no grand cosmic purpose to this timing. It's just an accident of when and where we happen to find ourselves in the universe's vast expanse of space and time. But it's a meaningful accident nonetheless. We're here, we're observing, we're wondering. And through that wondering, we're participating in something ancient and profound. The universe's apparent tendency to become aware of itself through the emergence of conscious beings capable of observation and understanding. We are matter contemplating matter, atoms arranged in such intricate patterns that we can observe other atoms billions of light years away and ask questions about what they mean. Webb's discoveries remind us of how extraordinary this capacity is, how unlikely, how precious. The early galaxies exist whether we observe them or not. They formed billions of years ago, according to whatever processes actually operated in the early universe, regardless of whether those processes match our theories. But the meaning of those galaxies, the questions they raise, the puzzles they present, the understanding they might eventually lead us toward, only exists because we're here to wonder about them. In this sense, Webb isn't just revealing the early universe, it's revealing something about consciousness itself, about the universe's capacity to produce minds capable of looking back across billions of years and asking, what happened? How did we get here? What does it all mean? These questions have no final answers. Each answer leads to new questions. Each mystery resolved reveals deeper mysteries beneath. The early universe was different than we thought. But why was it different? What processes operated then that don't operate now? What changed as the universe aged? We'll eventually develop theories that explain Webb's observations. But those theories will raise new questions about the even earlier universe, about the conditions immediately after the Big Bang, about why the laws of physics are what they are. The mysteries never end, they just become more refined, more specific, more interesting. And that's exactly as it should be. A universe that revealed all its secrets easily would be a disappointing universe. A cosmos that matched our first simple theories would be a shallow cosmos. The fact that the universe keeps surprising us, keeps challenging our understanding, keeps revealing unexpected complexity, this is what makes cosmic exploration meaningful. We're not just cataloguing objects in space, we're engaged in an ongoing dialogue with reality itself. A conversation that's been unfolding for as long as humans have looked up at the sky and wondered. Webb is the latest chapter in this ancient conversation. It's allowing us to ask more detailed questions than ever before, to observe further back in time, to test our theories against evidence from epochs we could previously only imagine. And what it's showing us is that our imagination, impressive though it is, still falls short of what nature actually did. The early universe was more productive, more complex, more surprising than we predicted. Our models, built from observations of the nearby modern cosmos, didn't fully capture the richness of cosmic history. This doesn't mean our models were useless. They were necessary steps toward understanding. They made predictions that could be tested. They organized our thinking and guided our observations, but they were incomplete. And Webb is showing us the gaps in our understanding, the places where reality diverges from prediction. Filling in those gaps will be the work of the next generation of cosmologists. Using Webb's observations, along with data from other telescopes and experiments, they'll refine our theories. They'll develop new models that better capture how the early universe actually behaved. And those new models will eventually make their own predictions, some of which will be tested and confirmed, some of which will turn out to be wrong, revealing yet deeper layers of cosmic mystery. This is the endless cycle of scientific understanding: observation, theory, prediction, testing. Each cycle bringing us closer to reality, but never quite reaching final, complete knowledge. Because the universe is not obligated to be comprehensible to us. It is what it is, whether we understand it or not. Our understanding is a gift we give ourselves through patience and careful observation, through the willingness to be surprised, through the humility to admit when our theories fall short. Webb's early universe observations are a perfect example of this process in action. We made predictions, we tested them, we found that reality was different than expected. Now we're revising our understanding. It's uncomfortable, it's humbling, and it's exactly how science should work. What makes this particular moment in the history of astronomy so interesting is that we're witnessing this process in real time. We're not reading about discoveries made decades ago. They're implications already worked out by previous generations of scientists. We're seeing the raw observations as they come in. We're watching as astronomers puzzle over what they mean. We're observing the scientific process as it unfolds. The massive early galaxies Webb has discovered will eventually make their way into textbooks. Future students will learn about them as established facts, part of our standard picture of cosmic evolution, but right now, in this moment, they're mysteries, puzzles that don't quite fit, observations that challenge understanding. We're living through the time when these mysteries are fresh, when the questions are still open, when multiple possible explanations are being actively debated. There's something special about this, about being present for the moment when new knowledge is being created, when understanding is shifting, when the map of reality is being redrawn. Most of human history has unfolded without any awareness of the early universe at all. The concept of cosmic history, of the Big Bang, of galaxies existing billions of light years away, these are all recent additions to human knowledge, emerging only in the last century. And now, just a few decades into our awareness of cosmic evolution, we're discovering that our initial picture was incomplete, that the early universe held surprises we didn't anticipate. How many more surprises await us? What other aspects of cosmic history will turn out to be different than we currently think? We don't know. We can't know. Not until we make the observations, build the instruments, look more carefully at what the universe is actually showing us. But we can trust that surprises are coming, that nature is more inventive than our theories, that reality will continue to challenge and expand our understanding. Webb is just the beginning. It's the most powerful telescope we've ever built, but it won't be the last. Future instruments will look even deeper, see even further back in time, observe the universe with even greater clarity. And with each new generation of technology, we'll learn more. We'll refine our understanding. We'll discover new mysteries that we couldn't have anticipated. This is the story that's been unfolding since the first human looked up at the night sky and wondered about the lights they saw. A story of endless curiosity, patient observation, and gradual understanding. We're part of that story now, living in a time when we can look across billions of light years and see the universe as it was billions of years ago. When we can test theories about cosmic evolution against actual observations of the early cosmos. The massive galaxies Webb has found in the early universe are real. They exist, or rather, they existed billions of years ago when their light began its journey toward us. What they mean, how they formed, what they tell us about cosmic history. These are questions we're still working to answer, but we'll figure it out through patience, careful observation, and honest thinking, through the collective work of thousands of researchers analysing data, building models, testing predictions. The answer might surprise us. It might require us to revise fundamental assumptions about how the universe works. It might lead us toward new physics we haven't discovered yet. But whatever it is, it will be true. It will be based on evidence. It will bring us closer to understanding what actually happened in the early universe. And in the meantime, we have the privilege of wondering, of sitting with the mystery, of knowing that the universe still has secrets it hasn't revealed yet. The early galaxies are out there, billions of light years away, carrying information about a cosmos that was different than we imagined. Webb is collecting their light, measuring their properties, building up a picture of what the early universe actually looked like. And slowly, observation by observation, we're learning to see the universe not as we wished it to be, but as it actually is. Strange, surprising, more complex than we predicted, but real, knowable, waiting patiently for us to understand it better. Tonight, as you settle into rest, perhaps you'll carry with you a sense of this cosmic mystery, an awareness that the universe still holds surprises, that our understanding, impressive though it is, remains incomplete. The massive early galaxies are still there, frozen in time billions of years ago, their light still journeying across space toward telescopes that might one day help us understand what they mean. And we're here, briefly, in this particular moment of cosmic history, conscious, curious, wondering about our place in a universe that continues to reveal itself in unexpected ways. The questions remain open, the mysteries persist, and somewhere in the vast darkness between stars, ancient light continues its patient journey toward us, carrying secrets of a young universe that was stranger and more wonderful than we ever imagined.